for monotonicity.
Hi, can everybody hear me? Okay. Hi, so I'll be talking about a type system for guaranteeing that functions are monotone. This is going to be really short because you probably already know it. It's the simply typed lambda calculus. But you have to view it a little differently. So first off, in order to even make sense of what I mean by monotonicity, I have to interpret types as coming with a partial order on them. So that's easy enough, right? Also, I interpret the arrow type as meaning not arbitrary functions from A to B, but only the monotone functions from A to B. And since my types need to be partially ordered sets, I endow them with the pointwise ordering. And if you do this, you're actually kind of done, right? This is a type system that will guarantee that things are monotone. If all of your built-in functions are monotone, then all of the functions definable in your simply typed lambda calculus will be monotone. But there's a snag, which is what about non-monotone functions? We might want to deal with those as well. And to deal with those, I'm going to talk about modal types. So in this case, what do I mean by a modal type? Well, I have this notion of modes, and a mode is just something that I can apply to a type that changes the ordering on that type, but not anything else about it. So for example, the mode up flips the ordering on the type. What was smaller is now greater. What was greater is now smaller. And the other mode that I'm going to be using is called box. And box throws away the ordering on a type. It just leaves you with reflexivity. No other less than or equal to relations hold. And so the interesting thing about box is, let's look at what it means for a function from box A to B to be monotone. Well, it means nothing. Because the precondition, right, is that x is less than or equal to y in box A. But that only holds if x equals y. And if x equals y, then of course fx is less than or equal to f of y. So we can represent arbitrary, potentially non-monotone functions as a special case of monotone functions. We just have to say that they're out of the box type. So this is great, right? We now can express fairly interesting relationships between the input ordering for some function and the output ordering that it's monotone in. And there's prior work on what the typing rules should be for box types. I called them modal types for a reason. But if we apply this prior work, we find that actually programming is kind of annoying, right? So I don't expect you to understand this code, but what the function is supposed to do is take a function from A to B and take a set of A's and produce, you know, map the function over every element in the set, produce the set of results. And this is monotone in the input set, because growing a set means adding elements to it. If we add elements to the set we're mapping over, we add elements to the result. But it's not monotone in the function you're mapping over it, and the function itself doesn't have to be monotone. And to convey that information to the type checker, we need all these annoying annotations. Really, we want to write it without any of those annoying annotations. We want to write this. This is the simple, nice program that wants to get out of our annoying annotated program. So can we make our type checker smart enough that it accepts this program? The answer is yes, I think. And the way that we do it is we use subtyping. So why would subtyping help here? Well, subtyping is fundamentally a way to convert between things of different types silently, without the programmer having to write anything, right? And that's exactly what I want to do. I want to have the type system figure out the conversions for me. And normally we think of subtyping, or one way to think of subtyping, is that it says that the identity function maps from A to B, that A is just included in B. But remember that we're in a world where we care about ordering. And so the identity function might actually have different modes. It might be a monotone map. It might be an antitone map, a map out of the opposite order. It might be just some map, we don't know anything about it, a map out of a box type. So just as the identity function can have many modes, subtyping can have many modes. This is the generalization of subtyping I use, right? So rather than just saying, is A a subtype of B, we find the mode T that makes TA a subtype of B. And this extra information gives us exactly the oomph that we need to type check our code without any annoying annotations. But I haven't proven it. So this is also only half the story. The other part of the story is I have this subtyping judgment that I've figured out. How do I adjust my typing rules to handle it? And to do that, I need various properties to hold in my modes, and one of the most important ones is compositionality. that if I have two functions, one from A to B with mode T, the other one from B to C with some mode U, right? Maybe the first one, F, is antitone, and the second one is monotone. There's always a mode that describes the behavior of the composition of those functions. And indeed, you can compose tones this way. I'm not going to show you what it is because I think I've actually given you enough information to figure it out for yourselves. So if you do think you've figured it out, come up and talk to me after the talk. So finally, I'd like to address the question you've probably been thinking for this whole time, which is why care about monotonicity? And the reason I've left this till the end is because I think it's actually the most important part of the whole talk. If I want you to remember anything from this talk, I want you to remember that monotonicity tames dragons. So here are 4 different examples of where monotonicity can be used to ban, or at least to help in proving that a certain bad thing does not happen. So a bunch of people out in Berkeley have this idea called consistency of logical monotonicity. And what this amounts to is saying that if your program is monotone in a certain sense, it's much easier to prove that it's eventually consistent, which means if you're running this program, on a distributed cluster of nodes, all of them eventually agree on the results. And that's a very nice property. And it can be very difficult to prove. Monotonicity makes it a lot easier. A similar, in concept, thing is that if you have a parallel program which gets scheduled non-deterministically, it would be nice if it always computes the same result. And there's been some work which has used monotonicity and some other properties to prove exactly this, that you can write a seemingly concurrent program, right, that can be computed, that can be scheduled in whatever way you like, but will eventually arrive at the same result. Finally, the thing I'm actually doing is working on recursive queries in a language called Datafun, which generalizes an earlier language called Datalog. And there, monotonicity is crucial for ensuring that recursive queries have a well-defined best answer. And finally, you may notice that there's a lot of classic logical paradoxes involving self-reference, such as Russell's paradox, the set of all sets that don't contain themselves. Or the liar paradox, this sentence is false. All of these involve self-reference, but they also involve negation, and negation isn't monotone. If you say that you can't use negation in a self-referential way, you actually turn all of these paradoxes into mere ambiguities. So in lots of seemingly unrelated fields, monotonicity turns out to be the key to avoiding unfortunate behaviors. So that's why you should care about monotonicity. Thank you.